Hello, everyone. Welcome to another seminar. Before I introduce the speaker, there's a sign-up sheet going around with only if you're taking the class, please put your name. There's always people, I think, who are putting their names are not in the class. I mean, you don't need to do it if you're not in the class. Okay, so it's my great pleasure to introduce our seminar speaker, Rahul Mazumder. He is an associate professor of operations research and statistics at MIT Sloan School of Management. He's also affiliated with MIT Center for Statistics and Data Science and the LIDS department at MIT. His research interests are the intersection of statistics, machine learning, and mathematical programming, which is large-scale convex and mixed integer optimization. He's a recipient of many awards, some of which include very recently the Leo Bryman Jr. Award from American Statistical Association, the International Indian Statistical Association Early Career Award, many Informs, Operations Research Awards. And personally, his research has been a very big influence in what I've worked on. It's been very inspiring. So it's great to have him here and for his presentation. So please welcome Rahul.
Thanks, Armin, for the introduction. And thanks to all of you for being here. And thank you for the invitation. So I'll be talking about simplifying complex machine learning models. So think of these machine learning complex ML models as random forest or XGBoost, which are usually used very commonly in a data science pipeline. We teach that in our statistics and ML data science classes. But usually these models tend to be very big, and it's very hard to gather insights from those models. All right, so the point over here is let's start from those models, which happen to be complex and very good in terms of prediction accuracy. Of course, I'm talking about large samples, a large number of data observations, fewer number of features. Let's start from those models, and then let's try and gather insights from them by simplifying those models, that is, making them smaller and compact. Okay, so that's one of the topics that I'll be talking about. And then depending upon the amount of time that I have, towards the end, I'll also touch upon other types of ML models, which are basically large language models, where simplification, the notion of simplification also arises for various different reasons. Okay, so in terms of tools, you will see that the models and the methods that we'll use, they have very deep origins in statistics. Okay, in fact, the entire problem of simplifying ML models, random forests, this has actually old roots in statistics, as I'll talk about. Okay, so let me first begin by acknowledging and a big thanks to my collaborator. So Brian Liu, he's currently a final year PhD student at MIT. So he has been doing a lot. He has been leading this effort on simplifying tree ensembles. And Peter Rajdenko, who has been a long-time collaborator from the University of Sydney. I will not be able to talk about the details, but when we talk about interpreting these models, we do these interpretations very closely with our industry collaborators, Amwell and Silver Cloud, which is a collaboration initiated by the MIT Sloan Health Systems Initiative. Okay. All right, so I'll be mostly focusing on this, but for those of you who are interested in LLMs and large neural networks, it turns out that the notion of simplifying a very large neural network also arises, okay, in problems that people care about, especially in industry. The motivation is very different though. And it turns out that very traditional statistical computational tools that we are used to thinking of in statistics, they turn out to be very useful in this setting. So, and this is a bunch of a line of work that we have been doing, mainly led by my students at MIT. Some of them have graduated and they are now in industry. And then this is a problem that we learned about from our industry collaborators, various groups at Google and then LinkedIn AI. So there are some references which are coming out of LinkedIn AI. These are publications led by LinkedIn about where these compressing models can be useful in the context of industry applications. So I'll be mostly talking about simplifying tree ensembles. So the context goes as follows. Many tree ensembles, such as random forest or gradient boosting, they are known to excel in terms of prediction. Bryman in his 2001 paper said that they are A plus predictors. They are popularly used in various domains, such as in finance, healthcare, and so on and so forth. And in terms of tabular data, they still show very strong performance compared to LLMs. Okay. So feel free to stop me at any point of time or interrupt me. I think that's how the talk becomes more engaging. So I have a bunch of slides. It's okay if I do not go to the end of the slide deck. Okay. So there are various types of packages out there in R, Python, Julia, and so on and so forth, which implement tree ensembles. So at a high level, if you think about what a tree ensemble does, it builds a collection of trees. Okay, so here is tree one, tree two, and let's say this is tree capital T, and then you add them. You combine them to form a tree ensemble. Okay, so I will be showing this picture a lot. So this basically means a collection of a bunch of trees. Okay. Now let's talk about the predictions. So for tree one, the prediction is going to be, let's say, tree one of X. This can be in a regression context. This can be, I'm predicting the continuous outcome. It's going to be Y hat X from tree one X. This is going to be the prediction for an input X from tree two. And this is the prediction from tree capital T. For the tree ensemble, I'll assume that the prediction is given by a sum of these trees. Okay, you can consider also a weighted sum, but let's consider something simple, just the sum of these trees. Okay, so this is basically the notation that I'll be using. Down the line, I'll talk about weighted sums and so on and so forth. But basically, by a tree ensemble, think of this picture: a large number of trees put together, and this is my black box prediction model. Of course, it goes without saying that tree ensembles are hard to understand. So let's say this is a data set on this is a general social survey data set from University of Chicago. We are fitting models to predict the household income using survey responses. This is a boosted ensemble, and a boosted ensemble, 500 trees, each of them of depth 6. Okay. So if I look at one particular tree over here and zoom in, this is going to look like a tree, something like this. Okay. So it's of course, I mean, this big black box, it's not really a black box, but anyways, this is a complicated ML model. This is actually hard to extract insights from directly. But if you look at some of the building blocks of this ensemble, one of the main building blocks is a decision tree. So let's look at the same data set. General social survey example. I'm using a decision tree. This is a decision tree where I'm predicting the household income using various types of independent variables that are given to me. So it comes up with a prediction. So this is the household prediction given this routing behavior. So the self-identified income class is less than equals to 2.5, as well as the spouse's education in years is less than equals to 14.75. This is going to be the prediction, and so on and so forth. Okay, so this is a decision tree. This is the graphical representation of a decision tree. And this is a rule-based description of a decision tree. Okay, so these two are equivalent. I will be using this notation very soon because I'll talk about rules. But basically, this is a decision tree graphical display, and this is a rule-based description of the decision tree. And this is basically written in natural language, right? In natural language, I'm using if-then statements to say, to explain this model, okay? And this is well known. As long as the depth is sufficiently small, then these are simple to explain. Okay, so since there are 4 rules over here, 1, 2, 3, and 4, one decision rule is given by 4 rules. This prediction can be explained by 4 sentences. All right, so now let's think about decomposing one decision tree into a collection of rules. Okay, so these are the different rules. I start from the root node and I go to the different leaves. Okay, so there are 4 leaves over here. They correspond to different rules. Okay, so from the node over here, I go over here. This is rule 1, this is rule 2, rule 3, and then rule 4. So I'm writing down these rules over here. Okay, so that's the notation of that's the definition of a rule that I'll be using in this lecture. It's a sequence of if-then statements. And if you follow the sequence of if-then statements, at the end, there is going to be a prediction. Okay, so the work that I'll be presenting is based on this paper. So I'll be spending most of my time on this paper. So it's extracting interpretable models. If you don't like the term interpretability, if you think it's too open-ended, think of this as simple models. So extracting simple models from tree ensembles. So this is the work that I'll be presenting in details. Okay, so let's think about this tree ensemble. The test R square is 0.55 and it has 32,000 rules. Okay, again, as a rule, you can think of this as a sequence of if-then statements. 500 depth 6 trees. It can be, there are basically 32,000 rules. So to explain this prediction, I need 32,000 sentences. You can say that instead of using this complicated ensemble, let's use one simple tree. Yes, that is fine with 4 rules, but the test R square over here is going to be much smaller compared to the to the prediction performance of this guy. Okay, so you lose a lot in terms of, you gain simplicity, but you lose a lot in terms of prediction capability. Okay, again, these are known statements. So the approach that I'll be presenting today, with that, you can get something like this. Okay, so let's look at this. So the test R square of the original ensemble is 55%, and the our approach is going to give an out of sample R square of 50%. So there is going to be a loss of 0.05, and this is a model. At the end of the day, you're getting a prediction model. It's given by a collection of rules. Okay, so every rule that you see over here is a sequence of if-then statements. So if you look closely, you'll see it says that if this variable is larger than 14.75, then the predicted income is going to be this. In this particular case, it says if the degree happens to be larger than this, and this satisfaction with financial condition is less than equals to 1.5, and so on and so forth, then this is what the prediction is going to be. So what I'm doing is, instead of using this complicated model, I'll be replacing this with this model, okay? And this model is given by a collection of rules. Every rule, as a reminder, is a sequence of if-then statements. And then at the end of the if-then statement, I'll be giving you a prediction, okay, a value of the predicted household income. What is a prediction from the rule ensemble? Let's make things simple. It's basically the sum of the individual predictions. So every rule is going to come up with a prediction. So the prediction of the entire ensemble, this is the rule ensemble, this is a simplified ensemble. The prediction of this entire rule ensemble is going to be the sum of the individual rule predictions. Okay, so this is basically the setup in which I'll be with which I'll be working. All right, now schematically, so you can think of this as I start over here, and our proposed framework is basically a computational tool, a framework with which I can go up to here. So here are some observations about this. You see that the different rules that you have, the rules can have different depths. We saw that over here also. This rule had a smaller depth over here, depending upon how you count. The depth over here is 2. The depth over here is 4. Different rules can have different depths depending upon how much complexity is needed. Okay, so that's how I'm describing complexity. The depth of the rule and the number of rules. In this particular case, I almost get something which looks like a tree. Okay, so if the rules are patched together properly, it is going to give you a tree. Okay. Right, so there are special cases of this framework. Some of the special cases are I can have a single tree. I can also do selection of rules where all the rules that are selected have the same depth. And also I can do depth pruning of trees, i.e. I had 10 trees initially. I will select 10 trees, but I'll control their depths. Okay, so these are all special cases. And I list them as special cases because down the line, when I'll be writing the mapping to go from here to here, there is going to be a constraint that controls the complexity of this family, of this class. And then special cases of that are going to give you a single tree, this or that one. Okay. And the point is that I want to get this framework in a general, this reduction, this compression should be done in a general way, so that depending upon the trade-offs, prediction accuracy as well as compression, I can get a model of this one. Questions?
a lot like you're just putting a lot of constraints on the original one.
Absolutely.
Why don't we just do that? Why fit this very complicated model and then simplify?
It's a good question. So various reasons. So one of them is computational. Fitting a model from scratch, which is simple, is actually hard, algorithmically hard. Okay. And there have been some attempts in this in the literature. The other thing is that in many of the data science pipelines, and especially this is becoming even more relevant now when you have these big companies training these gigantic LLMs. Those LLMs, think of these as black box, these complicated models that have been trained by an organization. So it can be an XGBoost model has been trained on millions of data points over several months because of hyperparameter tuning. Okay, that's your starting point. I'll take that as a starting point, and let's say there is a specific team that cares about ranking. Okay, they will take that team or pricing. They'll take that big model and simplify it for their specific task. Okay, so in many of data science pipelines, what happens is you start with a very big model to start with, and then you simplify it post-hoc, depending upon the application. So that's a very important question. Okay, all right. So prior work, as I said, this actually builds on a lot of nice work that has been done in statistics, especially Friedman and Popescu in 2008 and Meinshausen 2010. They wrote these two interesting pieces of papers. One of them is known as rule fit, and the other one is known as node harvest. So at a high level, you start with the original ensemble, and then you actually select rules from them. Okay, so there is no notion of depth controlling over here. So if the original ensemble has all the rules of depth 20, then the selected rules are going to have depth 20. Okay, no depth controlling is happening. Okay, so there are various variants of this. These are all, you can think of this as a post-training. A model has been trained, and on top of that, you actually do this. There are also their line of work, as you mentioned, it is training from scratch. And especially there is a line of work from coming up from very interesting optimization approaches. So they try and develop these rules from scratch under a budget on the number of rules that can be taken. So these are very interesting approaches, but computationally they become very hard because these are very combinatorial objects and scaling them up to large problems become challenging. There are also various other approaches on interpretable rule construction. There are also interesting approaches based on function trees, greedy additive trees, and so on and so forth, Bayesian additive regression trees, etc. There is also some work in the literature where focusing on depth pruning tree depth. So you have the original ensemble, you have a small number of trees, okay, and all that you do is you prune the depth, okay. So nothing else, no simplification of rules, you prune the depth. Okay. All right, so what we want to do over here is we are proposing a joint optimization framework and the reduction from a big model to a small model. This entire thing is going to be given by an estimation framework is given by the solution to an optimization problem. Okay, and the optimization problem is going to balance various things. Yes, there is a question. Say that again. Sorry, shallow. Oh, so what I mean is, so I'm not extracting rules on their own. I'm just controlling the depth of the trees. So every tree I get at the end of the day, I get a collection of trees. Okay, so of course, if I have a tree, I can split it into rules. Yeah. But if I get rules individually, they may not be, I may not be able to put them together into a tree. Okay, so that's what I said. So the focus over here is not on selecting rules, though that's a byproduct of this framework. Okay, so the flexibility of this joint optimization framework is, in words, what we do is we want to find out a compressed ensemble that retains the predictive accuracy of the dense ensemble to the extent possible. Of course, there might be a loss in prediction performance. Now you'll see that there is some kind of a correction that we do, because if you just trim a bunch of rules, the prediction power is going to go down a lot. So we do these adjustments by weighting. But again, there are limits to how much we can actually retain. I'll actually show you the trade-offs. So we want to retain the predictive accuracy of the tiny ensemble to the extent possible. The other part is simplicity or interpretability. We want this thing to be small, the extracted model. And then the other part is if you actually have a small model, it can be actually easier to store, easier to carry around. And then this is probably not a big deal in these types of applications, but there might be application domains for people who care about very high speed evaluation costs. If you have a small high speed evaluations or predictions, if you have a small model, predictions might be easier to do, faster to do. Okay, so what we will do is this entire formulation will set up as an optimization problem using discrete variables, binary variables. And it turns out that these, in order to scale to big problems, to big size instances, the algorithms have to be, new algorithms need to be developed. And there is also some statistics theory which where we establish prediction error bounds on a compressed ensemble. There is limited prior work in this setting in the prior in the literature. Okay, so now let me describe our estimator using math. So this is one decision tree. You have the different leaves, and what I'll do is I'll give a number to every node in this decision tree. All right, so this is decision. This is the node 1 in the decision tree. This is node 2 in the decision tree, so on and so forth. Okay, so every node is going to get a number, and the tree prediction, the prediction from this tree is going to be a sum of 4 rules. Okay, so MT4X means that for an input X, this is the prediction coming out from this leaf. Okay, so that's why I have the terminology 4 over here, because this leaf, which is node number 4, is doing the prediction. This guy over here, leaf number 5, this leaf, node number 5 is doing the prediction, and so on and so forth. All right, so MTIX is the prediction of node I in tree T. There are going to be, let's say, 500 trees. For every tree, I will be having a prediction function of this form. So for every tree, for every node, there is going to be a prediction. Okay. All of these are not going to be needed, but this is some notation that I need to develop my estimator, to describe my estimator. Okay, so let's say this is a schematic diagram for the tree ensemble. So over here, I have 1, 2, 3, 4, 5 trees. And let's say the simplified ensemble that I'll have looks like this. So from this tree, I will be selecting 2 rules. So this is rule 1 from this tree, and this is rule 2 from the same tree. From this tree, I'm selecting 1 rule, which is given by this sequence of if-then statements. This color that I'm using, this is basically giving me the terminal node, okay, that I'm using. From this leaf node, from this root node, I'm going to a terminal node, and these are the guys that are active. Okay, so these are the 2 rules that I'm using. Similarly, for this tree, only 1 rule is being used. This one, 1 rule, this one, 1 rule, and this one also 1 rule. Okay. So this is describing for me the selection. All right. So at what are the rules that are being selected? So this is describing for me what rules are being selected from this tree, at what depth. So that's the extracted rule set. And then this is the thing that I'm actually injecting now. I'm injecting new weights. I'm providing new weights. So if I do not use any weights, then there is going to be a huge loss in accuracy. So basically, there is going to be a big bias. I have to correct the bias, and that's why these weights are there. Okay, so that's basically what is happening. I start with the tree ensemble. I would need variables to indicate which of the nodes to use. And then for every rule that I select, for every rule, I need a weight. So the prediction that I get from this is basically the weighted sum of the rule prediction. So I have over here a collection of 6 rules, and the prediction that I'll get from this ensemble is going to be the weighted sum of the predictions of each rule. Yes.
I think they missed this, but for the first 3, why do we care about 2 nodes in the prediction?
Oh, so I'm saying, so this is a schematic. I'm saying I need a way to select what node to which node to select from the tree. These are all going to be selected by an optimization problem. Okay, so I'm just giving you an idea.
I guess you don't want to just select leaf nodes because that may just be too many, right? So you're allowing yourself to select any set of nodes.
That's correct. So actually, that's an important point. So if I only select leaf nodes, and then let's say my trees are of very big depth, have a huge depth, like 10. That means all the rules that I'll have are going to be of depth 10. The prediction accuracy of that ensemble may not be good. Okay. So maybe if I trim it a little bit, the prediction performance is going to be better. Okay, so this is the flexibility this is giving. Any other questions? Yes. Yes, that's coming up. Okay, so you're right. So basically over here, the goals are, there are two things. You're right, asking the right questions. So the estimator is given by an optimization problem. How do I find out the nodes that are going to be selected, and how do I find out the weights? Okay, so these are the things that we have to find out. So this is a decision tree. So these are going to be optimization variables. These are going to be learned from from the data, okay, via the model. So basically, you have binary variables over here. We are going to introduce binary variables, yes or no. Okay, so the binary variable is going to be on for a particular tree. T node I is going to be on if this node is terminal. Otherwise, it is going to be 0. Okay, and then the corresponding weights for each node. We need a weight also. Okay, so these are the optimization variables. Let's say over here I'm selecting this node as well as this node. So then these guys are going to be 1. Everything else, all the other binary variables are going to be 0. Okay, so this is how I'll be describing the small collection of rules. Okay, so now basically I get this rule as well as this rule. This is going to have a weight corresponding to it, and this is also going to have a weight corresponding to it. Okay, and these are binary variables. Again, I'm repeating myself, but this is going to be 1. All the other variables are going to be 0. In fact, all the other variables in this tree are going to be 0. So the point is, I want to learn what these binary variables are and what the weights are. Okay, so how do I learn them? So I set up an objective. This objective is least squares loss. So y can be the original training data points that I have, original training data points, or it can be a subset of the data, or it can be a calibration, separate data set. So think of this as a response. This guy, these are the predictions from the rule ensemble, from this ensemble. So this ensemble, the predictions from this, weighted sum of the rule predictions, this is given by this expression. This is given by this expression, and I want the least squares loss to be small. And here is a regularization term that we add on the weights. Okay. Yeah, so there are various types. For those of you who are familiar with distillation, y can also be the predictions from a big model. All right, so that's what is distillation. All right, so now I have to describe the fact that these rules are linked to binary variables. Okay, so that's the linkage constraint. So basically, in words, extracted rules are assigned a non-zero weight. So only the rules that I'm extracting, for only those guys, I'm going to be assigning a non-zero weight. Everyone else, the weights are going to be zeros. This is a pruning constraint. This is a constraint which says that is a valid pruning constraint. So basically, it says in words that if node I in tree T is set to be a terminal node, then none of its successor nodes can be set to be a terminal node. So if a particular node is a terminal node, the guys before it cannot be terminal nodes. Okay, so that can be represented with binary variables. This. So this is really the power of binary variables. The other thing is the attribute budget. So the attribute budget, there are various types of the various choices possible. AITs are parameters. You have to give me what the parameters are. So let's look at an example. So if I assume that all the AITs are 1, so these are parameters, let's say all of these guys are 1s, then this controls, the left-hand side controls the number of rules that are extracted. Okay. Now, since I have the flexibility to do depth pruning also, in order to get a good prediction model, what happens is some of the rules are going to be shallow. Okay, so some of the rules are going to be shallow, some of them are going to be deep. If all of them are deep, then the prediction accuracy is going to be bad. All right, so that's why some of them are going to be shallow, some of them are going to be deep, and that's coming from this guy, and this is controlling the total number of rules used. Again, this is one particular choice. There are other choices possible. So if I take these guys as, let's say I take AITs to be the depth of rule I in tree T, it is going to control the sum of depths. This is going to encourage shallow rules. And if I take AIT to be the number of features to each rule I in tree T, this encourages feature sparsity. So what that means is, let's say I have built a random forest model, which uses all the 100 features in my data set, all the 100 features. I want a compressed model to have a small fraction of features. Let's say 5 of the 100 features are being used. Then I will adjust this guy so that the number of features used is small. Okay, so depending upon the constraint, the characteristics you want in the compressed ensemble, you can express that or codify that via the different choices in AITs. Okay, so AIT equals to 1 is probably the most easy thing to use, where you limit the number of rules, and then most of the results that I'll show you are based on that. Okay, so if you put all these pieces together, this is your estimator. It's given by the solution to an optimization problem.
So you had the constraint, like the valid pointing was like about descendants of a terminal node, sorry, ancestors of a terminal node being 0. Descendants, would it, like in your examples, sometimes it wouldn't make sense to also have a descendant.
That's correct.
But that's not enforced here in your constraints, right? Descendants of a terminal node having 0, binary variable 0.
I think it should be encoded somewhere over here. This I cannot think off the top of my feet. I think
It's also
yes. What I do know is that if your trees are very deep,
yeah.
Okay, then the prediction performance is going to be maybe bad. So then the trees become shallower, and that is reflected via this loss function. So this loss function is implicitly enforcing trees to have shallower, the rules to be shallow. Okay, so this is putting together, this is basically the entire optimization framework, right? So it has in spirit, it has an objective, it has various types of constraints, and then these are the binary variables which are linking it to the various unknowns. That is the weights as well as what nodes should be used. Okay, so this is a family of problems which are known as mixed integer programming problems. So I mean, you have done some nice work on this integer programming family of problems. So these are basically optimization problems where this is a nonlinear. As you can see, the objective function is nonlinear. The constraints are all linear. But the reason why it is called mixed integer is because some of the variables are continuous and some of the variables are binary. Okay, so these are usually considered to be hard optimization problems. But the fact is that there is a lot of solvers out there and technology that you can actually use to solve these problems. So I will postpone the discussion of the algorithms. Before that, what I want to talk about is what do I do with this estimator? Okay. So usually a priori, I do not know how many rules to use. Okay. I may want to compress the model to 5 rules, 6 rules, 7 rules, and so on and so forth. That leads to what is known as a regularization path. So the regularization path is going to explore trade-offs, accuracy versus complexity. So this is a real data set. So there's a win data set. And over here, I change the number of rules on the x-axis, and then I have the out of sample R square. Over here, as you will see, if I have 3 rules over here, these are the 3 rules. Okay, so that's the simplified version of the complicated model. The R square over here, the dense model has a very big R square, like 70%. This model has 32% R square. Okay, so there is a loss. This is key equals to 7 many rules. Okay, and this is 39 many rules. This might be too complicated from an interpretation viewpoint. But if you look at these values, you will see the prediction accuracy basically saturates after a while. So basically around the level of k equals to like 15 or so, the prediction accuracy basically saturates. So there is a lot of redundancy that you see. So you're adding lots and lots of rules, but there is a lot of redundancy in them. Okay, and then this is again extracted completely from the data. Different data sets may have different types of regularization paths, as in the amount of compression that is possible versus the number of rules. Okay, and this is a place where the interesting discussions happen. That is, if a practitioner says that, okay, k equals to 7 rules is what I'll use because I am okay to take a hit in, let's say, 8.8, 0.8 in R square. Okay, that's the amount that I can tolerate in terms of a loss in accuracy. And this is the simplified model that I'll get. Maybe this is going to be too complicated in terms of interpretation, but still you can use this if you think of compressed storage or something from instead of using the entire big random forest ensemble, you can actually use this as a compressed version of it. Yes.
Is there a noticeable difference between which AIT and how fast the regularization saturates?
So over here, so that's an interesting question. Over here, I'm taking AIT to be 1. Okay.
Yeah. And in other cases, in your example of
So yes, that's a good point. So I think in some of the cases, if I take, for example, AITs to be the number of, I don't remember off the top of my head. But presumably you can assume that if I'm removing rules is basically a very simple building block. If I'm removing trees, for example, then the jump, I mean, it's going to be, there's going to be a big loss, and then suddenly it's going to go up. Okay. Okay, so performance versus other procedures. So this is, let's have on the x-axis model complexity. There is a number of rules. This is out of sample R square. And this is a procedure which is known as rule fit, which is a very well-known procedure, Friedman and Popescu, 2008. And this is the trade-off that you get. What this does is it selects rules from a tree ensemble. It selects rules and it uses it by a lasso procedure, okay, L1 procedure. This is a procedure where they build the rules from scratch by discrete optimization procedures. Okay, so this is a paper that came out in 2019, and this is the trade-off that you get. This is a procedure that we had, Brian and I, in a few years back, and this is a profile that you get. What basically this does is it uses non-convex penalties to do rule selection. It still does rule selection in the spirit of this procedure, Friedman and Popescu, but it uses a non-convex procedure to penalize the number of rules. And this is a procedure that we have. Okay, so basically you get better trade-offs, and this mainly comes from the flexibility that is there because you're doing both depth selection as well as rule selection. Okay, so I'll go over some of this quickly. So there are basically a lot of other experiments that we have done in terms of rule extraction. We compare our procedure on various types of data sets versus different types of procedures out there in terms of tree selection. So some of these procedures do tree selection, some of these procedures do rule selection. And mainly because of the flexibility that our framework offers, you often get better trade-offs, i.e., for a certain number of rules that you get, for a certain number of rules, if you put a budget on the number of rules that you can get, then the prediction performance, the accuracy tends to be higher. Okay, again, so these are very big, usually very big data sets, right? So the sampling variability is not that much as you would see with small amounts of data points. So here are some examples versus additive tree-based models. So this is a sum of tree-based sum of trees, and there are various procedures that are out there. One procedure is a sum of trees. BART, the Bayesian additive regression trees, is another procedure. Forest prune is basically another procedure that we had, me and Brian, and our method is a procedure over here. Okay, so different AITs, they actually, the different AITs actually influence various types of model characteristics. So usually feature weighting, actually, this was actually kind of interesting to us because we found out in some cases feature weighting, if you actually simplify the tree ensemble to encourage sparsity in features, it leads to better out of sample performance. Okay, so that we see somewhere over rule versus feature weighting. So you get better out of sample performance rule versus depth weighting. If you want the depths of the rules to be small, you could actually turn this guy on, and then you will get some of the trees. The trees are basically going to be are going to have shallower depths. The other part is model compression. Second, model compression is a proxy for interpretability, but model compression really it's about model compression. That is, how much of accuracy loss would you incur for a certain level of compression. So if you count something like the number of nodes in the full model divided by the number of nodes in the pruned model, then you see that this procedure that we have, which is our method, compression factor, that means bigger compression is happening for a certain amount, for a huge amount of compression, for the amount of compression that you get, for a large amount of compression, you will see the percentage decrease in test R square is actually small. So percentage decrease in test R square compared to the dense model. So usually what we found out is that the dense model has a very good prediction performance. If you're simplifying it, the prediction accuracy is going to go down. Okay. What we see over here is if you compress the model for a certain amount of compression, the loss in accuracy tends to be small. Okay, for this type of procedure. All right. So now let me spend a few moments talking about.
Like 6 minutes.
Oh, okay. So actually, I had misunderstood the time, but it's okay, no problem. So there are various types of algorithms. So these are so in terms of algorithms, this is basically a discrete optimization problem. And what we do is we have exact algorithms to solve this guy to optimality as well as approximate algorithms. And what is actually happening over here, basically motivated by this particular problem, which is basically a very familiar problem in statistics, best subset selection. So recently, people have been studying this problem and developing various algorithms for it to actually solve these guys to optimality or approximate solutions for this. It turns out that in the process, there have been a deeper understanding of various algorithms for this. And Min has also done some nice work in this area. And then over these algorithms are actually inspiring new algorithms for these types of problems. So at a high level, there are methods based on nonlinear branch and bound. There are methods based on outer approximation. I'm sorry. There are methods based on outer approximation, which is the procedure that we actually use over here. I'll skip through the details. In terms of runtimes, this is something that we can get. So basically, we can solve problems to optimality. This is like a discrete optimization problem. We solve these problems to global optimality using our proposed framework. So for a problem where the number of trees is 500 and the depth is 4, where we are dealing with 10,000 binary variables and 10,000 observations, we can solve the problem to optimality in around 58 minutes. Okay, again, so this is the statistics theory results need these proofs, need these optimality certificates. But from a practical viewpoint, perhaps the approximate methods are more practical because it's going to give you a good solution to the problem. And if you think about approximate methods, the approximate methods we can actually scale to much, much larger instances. So for example, for a problem of this form, number of observation is 15,000 and the number of binary variables is of this order. We can get approximate algorithms in around 5 minutes. Okay. Okay, so there is some statistics theory results that we actually have in terms of the prediction error bound. So this is it assumes an underlying model. So the underlying model, we do not assume how the underlying data is generated, i.e. we do not make any assumptions on what F star is. Is it a tree? Is it a collection of trees? And so on and so forth. That is basically encoded by these Oracle inequalities. And this F1 is an infimum over the random set, the constraints of the optimization problem. And depending upon the different choices of the AITs that you can get, you get different types of procedures, all right, different types of rates. So what else can we do with these extracted rules? So there are actually many other things that you can do with rules. Okay, and this is a place where people are excited about how would we make predictions by using large language models. And this is a place where we actually found out the following. So what is the following? That is, you can use this compression to actually get a textual representation of the tree ensemble. Okay, and why is this textual representation useful? Because if you're interacting with an LLM, the inputs should be usually in the form of text. So you can think of, instead of dealing with this gigantic blob of models, you can deal with this as a sequence of very small number of if-then statements. And if you think about the problem of where I have a data set where some of them are labels and some of them I do not have the labels, and I want to find out the predictions over here, and I want to do it with the help of an LLM. So this is a problem that people in the CSML literature are interested in. This particular procedure, that I'll mention briefly, what it does is it can use the procedure that I discussed to do a compression of the context. Okay, so I have this, I can fit a boosted tree ensemble to this. I can get distilled rules from this. And then these are the guys that I actually want to predict. So what I'll do is, this is the question prompt. So for these individuals, this is the radius, this is the texture, this is the area, this is the smoothness, what is going to be the value of the tumor. This is a question prompt. Along with the question prompt, I'll give it the distilled rule prompts. If you actually give these two things together, the performance of the LLM actually improves. Okay, and this is as opposed to giving it the information of the entire gigantic ensemble. So I think so. I'm basically running out of time. So there is this area of work where similar. I do not have time to talk about it, but there is this area of work where where these ideas can actually be used in the context of compressing LLMs or large language models. So this part I'll skip, and I'll move over to the conclusions. So basically, at a high level, what we saw is an example where we are constraining the complexity of large ML models in a certain pipeline. A large ML model is already out there, and I want to simplify it. It can be to gather insights from the data set, or it can be to simplify it for computational reasons, and so on and so forth. There are various types of use cases for it. It can be tree ensemble, the ones that we see in classical ML. It can also be in the context of compressing LLMs. Okay, so this I didn't have time to talk about. And then there are interesting questions over here at the intersection of computational stats, optimization, as well as methodological statistics. And we need ways to understand the trade-offs in complexity, interpretability, as well as model accuracy. Some of these things, techniques that we are actually developing, they can actually have implications for other tools also. So for example, we all use lasso solvers or L0 type solvers, sparse regression. Some of these questions may arise, that is, how do I develop GPU accelerated versions of it? All right, so this is more relevant to the foundation models LLMs now. But there are some interesting consequences of this beyond the specific use case of compressing models. So with that, I'd like to thank you for your attention.
Any questions?
Something very basic that so when you have a tree, the rules that are based on this tree partition the entire feature space.
That is correct.
Now you have a new position for a given rule.
Absolutely, no.
It covers the confirmation. The only way to move that conform with the confirmation.
So it is correct. So in the case of a decision tree partitions the entire X into regions. Every data point goes in is going to go to exactly one of the rules. The rule collection that I have, it is possible that a data point does not go through any of these. In that case, the prediction is going to be 0. Okay, and I'm actually assuming that the data is standardized. Right? The data is standardized. So I'm taking out the needs. Okay, this is actually one of the issues. So it is absolutely possible that a data point does not go through a single rule. In fact, another thing can happen. The other thing can happen, that is, if I have 5,000 rules, for example, it can happen that a data point is passing through all the 5,000, which might hurt the prediction. Okay, but yes, you're absolutely, you made a very nice observation. That is right. It's one of the characteristics of this species.
Any other questions? Maybe one more if there's something. Yeah.
Looks to me that this would be really useful for transfer learning or something, people was going to talk about dealing with it for a new data set, for
Right.
a new law here. And I wonder, trying to re-estimate the read and what that means.
Yes.
Is there a shortcut to that, maybe where if I just could characterize the difference in the these people? I could learn something about how short that calculation.
It's actually a good question. I do not know the answer to the shortcut. I do not know that. But mechanically, the way in which it is actually ideally set up for that transformer. So I have a model, a very big model that has been trained on whatever knowledge, and you have your specific data set. It can be private data, for example. On that private data, what I can do is I can actually solve that optimization problem on the calibration data set, on that private data. And then simplify. Actually, so yeah, so then the reconstruction is going to be private. So all that I know is we actually have to solve that. That's one thing. I do not know of a way in which you can avoid solving that. Maybe it is possible. Okay, but it is developed for with those applications. It can be a solution like transfer.
All right, let's thank the speaker.